This video will present solutions to the 2018 VCE Mathematical Methods Written Examination 2. Section B, Question 1. Question 1. This question has us considering the quartic function f of x. Looking at what comes ahead, it seems like we're going to perform a number of computations upon f of x. Hence, it's probably worth defining it on our class pad. Right, now that that's done, let's get down to business. Our first computation is to find the coordinates of the point M, where M is the minimum value of the function. I'm going to compute this using the fmin command. Giving us coordinates x equals -2 and y equals -32. Part B. This concerns the graph of y equals f of x plus b. This would be a vertical translation of the graph we can see above by b units. If this graph was to have no x-intercepts, we would want to vertically translate the graph we can see 32 or more units upwards, as that would move the point M to above the x-axis. Hence, our value of b must be greater than 32. Part C. To find the equation of the tangent L, I'm going to use the command tan line on our function f of x. The tangent we wish to draw emanates from the point -1/3. Hence the equation of the tangent will be y equals 80/9x plus 41/27. Part D. We now wish to find the other 2 points where this tangent intersects the function f of x. So we're interested in solving f of x equal to the equation of the tangent. And this equation can be solved on our class pad. This provides us with 3 solutions. The initial solution is the point of tangent C. The other 2 solutions would be x equals minus square root 42 on 3 minus 1/3, and x equals root 42 on 3 minus 1/3. Looking at the form of the solution that is required, we can rewrite our solutions in the following way. X equals -1 plus or minus the square root of 42 all on 3. Part E. In this part we are asked to find the total area bounded by the tangent and f of x. Looking back at our graph, that will be this area and this area, which we can find by integrating from the first intersection point to the last, as the tangent lies above the function across that whole region. This area can be found by integrating from -1 minus root 42 over 3 to -1 plus root 42 over 3 of the line L minus the function f of x. We can compute this definite integral on our class pad. Here's our line L minus our function f of x. There's our lower bound. And here's our upper bound. Now that output is far from the form required, but tapping simplify, it is reduced to the form that we require. This question now turns its attention to a function p of x. Once again, this function, also a quartic, seems to be used a fair bit in the following computations, so I'm going to define it as well. With that done, let's have a look at part F. Part F asks us to consider when p of x is equal to f of x. To do so, it's probably worth remembering what f of x is equal to. Looking at the expressions for f of x and p of x, we can see that they have the first term and second terms equal. So our question really revolves around the minus 12x squared term and also the terms minus 12ax and a squared in the function p of x. Looking at these expressions, we can see that a value of a equals to 0 would satisfy the equality of the constant term and the linear term, and with a little checking we can see that it will also satisfy the minus 12x squared term. So that gives us our value for a. Our next computation requires us to solve p dash x equals 0. This is a computation I will be doing on my class pad. This computation gives three solutions for x. X equals 1, and looking across a little, x equals minus 1 plus or minus the square root of minus a plus 1. In part H, we are asked to consider when p will have only one stationary point. That will be when the solution for p dashed equals to 0 has only one solution and not three. For this to occur, our second solution, x equals minus 1 plus or minus the square root of negative a plus 1, needs to not exist. If this is to happen, we need to focus on the square root of minus a plus 1. This will not exist when we are square rooting a negative number. In other words, it will not exist if minus a plus 1 is less than 0. This means that minus a must be less than minus 1, and so a must be greater than 1. H part 2, we are asked to find the minimum value of p when a equals to 2. This is a computation we can do on our class pad using the fmin command given the value a equals 2. with this calculation providing us with a minimum value of minus 13. H part 3. If P of x has only one stationary point, then that means that A must be greater than 1, as we found above. Now, let's think about when P of x equals 0 has no solutions. That would mean that P of x with its one stationary point would look something like this, and we want this to occur above the x-axis. The turning point will therefore have coordinates 1, P of 1, because we know when we have only one turning point, it has the value x equals 1, as we found previously. And if we want this turning point to be above the x-axis, then P of 1 must be greater than 0. And so we're interested in P of 1. This is a quadratic in terms of A, with a leading coefficient of 1. Knowing this, we can find when it's equal to 0 and hence decide when it will be greater than 0. This allows us to draw a sign diagram for P of 1. The values of A we require will fall in the region A greater than 3 plus root 14, as it must also satisfy the requirement A greater than 0.